Good morning, good afternoon, everyone, and welcome to the Rotary Club of London meeting for Monday, March the 21st, 2022. I will now call upon Malcolm to introduce our guest speaker for today.
Thank you, President Don. On Christmas Day 2021, NASA's James Webb Space Telescope, an infrared space observatory, launched from Kourou in French Guiana at 7:20 a.m. on board an Ariane 5 rocket. The telescope was wrapped up much like a butterfly in a cocoon to head off into space. This 10 billion telescope project is NASA's largest and most powerful space science telescope, and it's going to probe the cosmos to uncover the history of the universe from the Big Bang to alien planet formations and beyond. It is one of NASA's great observatories, huge space instruments that include the likes of the Hubble Space Telescope to peer into the depth of the cosmos. It took 30 days for the telescope to travel nearly 1.5 million kilometers to its now permanent home, a gravitationally stable location in space. Our speaker today is Els Peeters, part of the NASA team working here in London at Western University, to tell us more. Welcome, Els.
Thank you very much, and thank you for inviting me to talk to you about this exciting project. So, as Malcolm was already saying, I'm going to talk about the James Webb Space Telescope. It is a project from NASA, the Canadian Space Agency, CSA, as well as the European Space Agency, ESA. And the James Webb Space Telescope, or JWST, as I will call it for short, is the most powerful space telescope ever built. And it was about 10 million. It took us years to build, but we are now very close to having it fully operational for science. I may add to this description is that's probably also the most complex system or object that was ever built by humans. And so in that sense, it's very, very exciting. And so let me introduce you why James Webb is so exciting for astronomers. And so the first thing to talk about in that respect is to talk about the electromagnetic spectrum. And so when we look at light, our eye is only sensible to a very small part of the light that is emitted by various objects. And that is shown here in this figure by the rainbow colors in the middle. But you can see that on both sides of these rainbow colors, we also have other types of light which have different energies. And you can go to higher energies, and then you can go to X-rays, you may be familiar with from the medicine, or you can go to the longer wavelengths, lower energies, where you go, for example, to microwave and radio. And so when we are talking about the James Webb Space Telescope, we are going to zoom in here in the infrared. And so those have wavelengths you can see here, similar to a needle point. And that corresponds to typically temperatures or objects of about 100 Kelvin. For example, the Earth will emit very strongly in the infrared. And so you may have heard about the famous Hubble Space Telescope already, or have seen these awesome pictures. And so JWST is very often called the successor of Hubble. And so what does that mean? So if you look at the electromagnetic spectrum, here is another figure illustrating it. You can see here once again the rainbow that we can see with our eyes. And so this area here, the rainbow, and some area to the left of this rainbow was the area that could be observed with the Hubble Space Telescope. So the Hubble Space Telescope mostly looked into the visible and bit on the ultraviolet and near infrared, and gave us wonderful pictures. The James Webb Space Telescope, in contrast, will look more to the red of our rainbow colors here, and we're going to look in the infrared. So we are detecting light which have a different energy, a lower energy than what Hubble can see and can still see. I mentioned here also another telescope. It's a Spitzer Space Telescope. It's one of the other NASA's great observatories, and that was also functional in the infrared. And so many of the comparisons that I will do in this talk is either with Hubble, because that is probably the most well-known telescope by the public, but I will also make some comparison with the Spitzer Space Telescope because its wavelength range or the energies it can detect is more similar to those on James Webb. Another thing to keep in mind is when we compare those three telescopes, I show here you the relative size of the mirrors. And so Spitzer mirror was very small, but if you go to the Hubble mirror, you can see its diameter slightly larger than a typical size of a human being. And then we have the mirror of JWST. It contains 18 individual segments, but working together, it has a diameter of 6.4 meters. And why does the diameter matter? You can think about it as a bucket. Okay, if you have a bucket with a small surface area, or if you have a bucket with a large surface area, the one with a large surface area is able to collect more raindrops than the one with a smaller surface area. And so the larger the mirror, the fainter objects that you can detect if you observe for the same amount of time with the different mirrors. And so in that sense, JWST is very, very sensitive and is able to detect much fainter objects that we have basically not detected to this point. And why do we want to go in the infrared? Here you see on the left a Hubble image from a famous star-forming region, and so we're looking in the visible, so we see many, many stars in the image, but you can also see these three pillars here where you see that there is slightly fewer stars present. If you look at the same image in the infrared, you can see a completely different view. And so why you can see now that these pillars are more prominent. We see very few stars anymore, and we basically are able to investigate what these pillars are and what they are made of. And so if you look at the same object with different telescope, what will happen is that the telescope will be able to observe different types of light with different energies, and that allows you to probe different parts of the region or different processes that are happening in a region. And so if you want to look, for example, at the stellar component, you could go very easily with an optical image. If you want to look at stars that are still being born, you basically mostly go to the infrared. We also want to go in space if we want to observe in the infrared, and that's because of the Earth's atmosphere. And so here in the bottom, you can see the Earth's atmosphere, and we are here where we once again can detect the visible light. And so visible light can basically penetrate the Earth's atmosphere, and we can see it here on the ground. However, if you go to the infrared, so more this region here, you can see that the atmosphere blocks lots of the radiation. And so if you want to have a complete view of all infrared light, you basically have to go to space, because from the Earth, you cannot detect it with ground-based telescope. Infrared telescopes also need to be cold. The reason for that is any object, even we, will emit light. And so if you have an object and you put it under a detector, you can see or detect the light it's emitting. And here you have two glasses. On the left, you have a warm glass of water, and on the right, you have a cold glass of water. And you can see that both are radiating, but the one in the cold, and the one on the left, the warmer one, have clearly higher temperatures, so at higher energies, while the one in the on the right, the cold one, has lower temperatures, and therefore we need to go to lower energies when we want to detect it. Now, If we want to detect the infrared light from a famous star-forming region, for example, we want to make sure that what our detectors see is the light from that region and not from the telescope and not from the instruments. And so in order to do that, what we need is we want the instruments and the telescope and the mirror to be cold enough so that the light they emit is not significant at the energies that we are operating with our telescope. So we want to detect only the light from our object in space, and we don't want to detect, or at least diminish it as much as possible, the light from the telescope itself. And for that, you need to cool down your instruments, because when they're colder, they're going to emit their radiation at lower energies. And so you want to put your instrument as cold so that the energies that they emit at are no longer detected by the instruments. And you can see the emission from your region in space. And there are different ways that we do that with the James Webb Space Telescope. If you go to the beach, you want to be colder, you go and sit under an umbrella, and we do exactly the same with the telescope. So what do we have? We have our telescope here, and on one side of the telescope, we have a sun shield. That sun shield is as big as a tennis court. It is 6 layers with air or vacuum in between. And the telescope is positioned so that the sun is always on the same side of the telescope. And so you can see that here. So our telescope, as was already mentioned, is traveled far away from us, 1.5 million kilometers to a particular point in space. And there it's in such a configuration so that the Earth, as well as the sun, which is off the screen here, is always coming from the same side, always seeing the same side of the telescope. And so that means on that side of the telescope is warm. It's about 85 degrees Celsius. While on the other side of this big sun shield, the telescope is cold. It's minus 233 degrees Celsius. So very, very cold, because we want to observe in the infrared. And so all our telescope instruments, as well as the mirror, is on this side of the sun shield and is very cold. For most of our instruments, this configuration is sufficient to be so that it's cold. The instrument is cold enough, except for the instrument which is observing at the colder energies. That instrument is cooled actively. And so it will have to go down to minus 267 degrees Celsius. So about 14 degrees Celsius lower than the other instruments. Canada has contributed significantly to the James Webb Space Telescope. It has contributed one of the science instruments. It's the near-infrared imager and slitless spectrograph. It's also contributed to fine guiding sensor. And this fine guiding center is basically needed to be able to point the telescope at a certain object and keep it stable at that object, so we can do our science observations and we don't get a blurry image. As was mentioned, our telescope has a mirror of 6.4 meters. And so it was folded up in space. And so once it was launched, the first thing that needed to happen is basically unfold the mirror. And as I mentioned, our mirror consists of 18 different segments. Once the structure is unfolded, you have to align all of these 18 segments so that they form the perfect image. And so when you turn on, when you look with your telescope for the first time, this is the image that you get. And you see 18 images of a star, but they're kind of on a random pattern, okay? And now what you have to do is each of these mirror segments, you can move them, okay? You can tweak them, change the angle, change the height. And so you tweak them until they form this type of pattern. And then once this is the coarse alignment of each of the segments, then you go to a much finer segment, a finer alignment, so that you have a focused image of from all of these 18 segments. And then the next step is you want each of these mirror, you move it so that the star basically falls on top of each other on the detector. And so that's happening in the last couple of weeks with the mirrors. And now, actually, just last week, Wednesday, NASA released this wonderful image from just a very bright star close by. And you can see here the star. These spikes that you see here are due to the fact that the way our telescope is built, you have some diffraction, so some of the light get bended and produces these artifacts. But everything else that you see in this figure are basically galaxies. And you may not at this point think that, well, I've seen this with Hubble. Hubble also looked at a star and has also galaxies in the past, in the distance. But I would like you to show you a comparison. And for that, I need to switch my screen for a second. And so this is an image that was shown on Twitter recently. And so what you see here, it starts with an image of the Spitzer Space Telescope, which was the prior infrared telescope. Okay, so it's looking at the same energies. And then it moves into the image that was just released from James Webb. And you can see the first image is very blurry and everything is kind of, smoothed out. And then you go to the image from the James Webb Space Telescope and you can see the amazing details that we expect to see with the James Webb Telescope. And so every little dot that you see here are, in the final image are galaxies, and you can see that some of them you can barely see with the previous instrument. And so that alone, it's the combination of having sharper eyes as well as having this big bucket, big mirror, so that you can see fainter galaxies, gives you the amazing advancements that JWST will give astronomers. And I had to include this one in the telescope. They can also make selfies. And so this is when you look from the secondary mirror back to the big mirror, and you can actually see the telescope. And these black lines here are the supporting structure from that secondary mirror. And so all of this is, this image is absolutely fascinating. This is just a calibration image showing that all the 18 segments are perfectly aligned for one of the instruments, and that alone, it's a short exposure. It's already much better than we have seen before. Because James Webb is so much better as before, I showed you this image, but all of the instruments, there are 4 instruments on board, all of the instruments are at least an order of 10 better than their predecessors. And so that means in astronomy that you will discover new things for any area, okay? James Webb can look at galaxies that were about 100 million years old. And what does that mean? Hubble could look at galaxies that were, toddlers, okay? James Webb can look back further and they can look at babies. And that's because of that big mirror, okay? You can look at fainter stuff. You can look, that means if a galaxy is further away, it's fainter. It's the same as you have your flashlight and you put it further away from you, it will look fainter. And so James Webb can look further away, can look farther away from us. It also has much sharper eyes. As I said before, that video, you go from blurry image to a very sharp image. That's the sharper eyes. And that allows us to have a discovery space, even if you're looking at objects very, very close by. And because JWST is so revolutionary for astronomy, NASA has made a special category of early release science programs. These science programs, they will be observed first thing that JWST will do science, okay? And these data will become public immediately because the astronomical community can then see how amazing how revolutionary the telescope and the instruments are, and then figure out what's the next proposal they have to write for which science question they want to answer. And so I'm leading one of the 13 early release science program, and we are looking, or our official title is Radiative from Feedback from Massive Stars. And I would like to talk a little bit about what we're going to do with this program. And so we're not going to look at very, very faint galaxies. We are going to look very, very close by, and we're going to look at the Orion Nebula. And you may have seen Orion on the sky already. And so if this is a Hubble image of Orion, and so the Orion Nebula is the nearest massive star forming region. It's very bright, and it's has many, many, many young stars. It's a stellar nursery. And if you look very often to Hubble images, you may have come across to this image over here, for example, and you can see in these little insets different areas where stars are being born. Okay, and you can see that they're all have very different shape, and some have, you know, here it's kind of a black. There seems to be a little disc here that blocks the light. Remember, this is a Hubble image, so it's invisible. And so we are going to look at star formation, and in particular, we are going to look at the heart of the Orion Nebula, here in the middle. And in the heart of the Orion Nebula, you have the trapezium cluster, 4 very, very, very bright stars. And these bright stars, of course, emit lots of radiation, and that radiation changes their environments. And it will influence their environment. And you can think about when you go camping in Canada in the winter, okay, you are cold, so you make a little fire. And that fire, of course, also emits radiation, and the snow very close to your fire will melt because of the radiation, okay? In space, exactly the same thing. Those 4 stars will emit lots of radiation. The neighborhood in the picture here was snow, but here, of course, we have all kinds of material in the neighborhood, and that material will change because of that radiation. And that's exactly what we would like to study. So in the surroundings of these stars, these are young massive stars. There is basically the cloud out of which the star is formed. This cloud is a mixture of gas and dust. And so that gas and dust reacts to the radiation. And that's what we want to study. And why do we want to look at it? Again, at Orion. Orion is very popular. Astronomers have looked at it many, many times because JWST is very sensitive and it has very, very sharp eyes. And I will show you in a second why that matters. By looking how the radiation changes the cloud out of which these young stars are formed, we can learn something about the formation of stars and planets. And we can also learn something about how galaxies ages, because star formation occurs not only in our Milky Way, but also in other galaxies, and it changes how a galaxy evolves. And understanding star formation is a very big key question if you want to know how galaxies evolved. And so we are going to look at Orion. We're going to look in the infrared. Why in the infrared? Because we want to look at these colder energies. And as for the image that I showed earlier, if you go to in infrared, you're going to look to star forming regions. You're going to look at colder dust and gas, but you also be able to peer through the dust. If you look at firefighters, if they go into a house with smoke, they put in infrared goggles so they can look through the smoke. And so that's what we're going to do here. Orion is studied to that by the Hubble Space Telescope, but Hubble cannot look through the dust. JWST will be able to look through the dust. And if you look at young stars that are still being formed, they're surrounded by a lot of dust. And so you go to the infrared. How do we learn? We will take, of course, pretty images so that we can share that with everyone to be excited with, but we will also take spectra. And what is a spectrum? You're basically going to see for every color that you have, how bright it is. And the reason why we do that, because this type of information, this spectra, reveals what the composition is of the gas and the dust out there. It's the same as a fingerprint, okay? If every human has a unique fingerprint, if you look at different elements, hydrogen, sodium, helium, etc., you see that they emit at different colors. And so by taking a spectrum, you can see which of the elements are present in the region that you're looking at. And so that's the way you can study what the composition is. And remember, our goal was to see how the environment changes because of the radiation. So we need to figure out what the composition is with distance from our stars. I mentioned JWST has very sharp eyes. Remember that picture? With the prior telescope, we would see something like this in Orion, and with JWST, we will get the full picture. The sharpness of JWST's eyes is sufficient for us to probe it. It's detailed enough so that it's similar to the scale at which the processes that change the material occur. And so that's the first time ever. So here again, our trapezium cluster, we're going to look at this particular region here, and we're going to follow this yellow arrow. Okay, and you can think of a layered cake, okay? Close to the star, you have the purple region. Further away, you have the blue, the green, etc. Okay, and every layered structure of your cake will have emission that is different because the composition of that region is different because of the radiation. And with the Spitzer Space Telescope, you got all in one single pixel. So all of these layers were mixed. And so we had to figure out what was going on, and which is very difficult if everything is mixed together. You know, it's like in the old pictures where you took a picture of a crowd with an old camera, a face, maybe 2 pixels, and you couldn't tell if the eyes were blue or brown, for example, okay? The same here, everything is mixed with the prior telescope, but with James Webb, we have a tiny pixel size, very sharp eyes, and so we can see how things changes with distance from the star. In addition, the Orion Nebula has the ideal orientation. Here I have a very beautiful image that I took from the web. And you can see, if you look to the image from this side, we can see green on the left, gray in the middle, and red, blue, purple on the right. Okay, and all of these layers are singular. So on one side, we only see green, then only red, gray, and then blue. If you look from the other side, next to the image, from every position that you look, you get all colors. You first see the green grass, then you see the gray road, and then you see the house behind it. Why does it matter? Because we want to study how things change with distance from the star. And then we cannot do much with this, because then once again, everything is mixed, even with JWST sharp eyes. We want to look in a configuration like this, because then you can see how things change under the influence of the radiation from the star. And we can probe the layers of our cake. And so that's what we will do. Our Orion is visible with JWST in September. And so we are very excited to receive our first data and be able to understand how starlight changes its surrounding, and therefore it tells us a little bit more about the process of star formation and planet formation, as well as how galaxies evolve. So I thank you for your attention. If you are excited by James Webb, there are 2 awesome web pages where NASA updates all the information about Webb. One is, if you Google "where is Webb," you automatically go to an awesome website that tells you what's happening right now with the telescope. And there is also a blog on Webb that gives you more extended articles on different aspects. Thank you.
Well, we will open up for question and answer now. So if you have a question for Els, please use the reaction button on Zoom and just raise your hand and we can ask Els your question. So Dicey, Malcolm, you had your hand up first.
I did. Thank you, President Dunn. So you use this term dust. Do you know what physically size that is? It dust like a rock size or actually like pebbles of sand?
Yes, so the dust that we're looking at, you can think of the dust that you find on the beach, you know,
Okay.
micron sized.
And where did it come from?
That's a very good question. So when stars grow old, at the end of their life, when they're, you know, when they're very massive, they just explode. But when they're lower mass, what they do is they expel their outer layers. Okay. And so these layers kind of are basically expelled from the star and therefore cool down, the temperature drops, but it still has a fairly high density compared to the density that you find between the stars, no? And so that means in that expelled material, the temperatures at some point will be cold enough for elements to condensate and form dust. And so that's where you form dust. And over time, this expelled material basically travels further away from the core of the star where it was expelled from, and eventually becomes part of what we call the interstellar medium, the region between the stars.
Sure. Thank you.
You're welcome.
Els, will James Webb be able to explore other galaxies? And my second question is, how many galaxies are there? Or universes, or whatever you want to call them.
Billions. I don't think we have a good number of the total amount of galaxies, because so far with our current instruments, we could only look back to, let's say, the toddler stage. Okay. And so you may have heard about the Hubble deep field, which is basically an area in the sky, and Hubble looked for hours and hours and hours to the same area in the sky. And the reason why we do that is because if you have your bucket, okay, and you keep it outside when it rains, if you keep it outside for a longer time, there's more water in your bucket. And so with a telescope, it means that you have more photons coming in from the region that you're looking at. And so if you look longer, you can detect fainter stuff. And so Hubble could look back to, if you compare, you know, the age of the universe to a human life, Hubble could look back to galaxies when they were toddlers. And so JWST will look back even further down to more baby-like galaxies. And so, yes, one of the four main science pillars for James Webb is looking at the earliest galaxies, what are their characteristics, and how do they evolve into what we know of galaxies present day. And so this is completely uncharted territory. But JWST will look at exactly the same spot on the sky as Hubble and look at it for many hours. And then we can complement what we learned from Hubble deep field with what we will learn from JWST deep field.
Okay, do you know the age of our universe?
13.6 billion years.
Are we considered a toddler or?
No, so we are living, so our universe is 13.6 billion years old right now. And so this is where we are now, okay? We as humans. And so when I make that comparison, so the other way to think about this, we are not right now on December 31st, okay? With the current universe. And we go back, when the universe formed was January 1st. And with James Webb, we can look back in time to galaxies that are currently on January 6th. And with Hubble, we could, I don't know the exact date, but we could only look back till, let's say, end of January or early February.
Thank you very much.
Howard, you had a question.
It might have been partly answered, but my question was, you say that the telescope is looking back into areas where stars are being born. So is that still ongoing, or are you looking at things that happened in the distant past?
You're actually looking at distant things in the distant past, because you have to think, okay, we are here, you know, on the scale of the universe, JWST is very close to Earth, okay? So let's say we are here at some point, and when we detect light from a galaxy, that light has to travel towards us, okay? It takes time. Like if you go from here to Toronto, it takes time for you to go and drive to Toronto, 2 hours, roughly, okay? And so if you detect light from a galaxy, it took light time to travel from the galaxy to us. And so that means if we look at the galaxy right now, we receive light that was emitted a certain time ago, okay? And so if your galaxy is further away, it takes more time to come to us and fall on our detectors. And so we are, in a sense, looking further back in time, because the light that we today receive from the galaxy was emitted when it was younger.
Okay, thanks.
Does that make sense?
Yes, it does. Yeah.
Kirk, you had a question.
So, what is the expected lifespan of the Webb? And my final question is there any danger of space junk damaging it?
Those are very good questions. So the required time for James Webb lifetime set out prior to launch was 5 years. We now know that Webb will probably, if nothing goes wrong, function for more than 10 years. And so there are two factors that determine the lifetime. The first factor is the fuel. There is some fuel aboard of JWST, and once you run out of fuel, it's the end of the story. And so for what do we need the fuel? We needed a little bit of fuel to bring JWST to where it's living right now, L2. But because the launch with the Ariane 5 was perfect, and JWST was launched in the perfect orbit, we used less fuel to bring Webb to where it is right now. And so we used less fuel. That means we have more fuel left over. And so during the mission, you need a little bit of fuel to keep Webb where it is right now. And we also need a little bit of fuel because when the sunlight hits the satellite, it gives some momentum to the satellite, and we have to offload that. But because the launch was so well, we currently have fuel for, I think they said 20 years. Okay, so much longer. Now, of course, at some point things will break, and so that will probably be the limiting factor. With respect to the space junk, the major issue is that we have this big sun shield, which is as big as a tennis court. And so there's a lot of junk out in space. And there's also just, asteroids and meteorites, etc., in space. And so they could hit the sun shield. And we need the sun shield to cool the telescope. Now we have 6 layers, so we have some buffer. But at some point, yes, I'm sure they have models about it. I don't know, I haven't read upon that. But if the sun shields is no longer functional, your telescope, your instruments, your mirror will warm up, and you can no longer observe in the, well, you will observe in the infrared, but you will observe the radiation from your instruments and your mirror, and not from objects in space.
Luis.
I'm going back to the Orion Nebula. You were talking about hot gas and cold dust. What temperature would that be at? Like the gas?
Yeah, that's a good question. So close to the, so our stars have a temperature of about 40,000 Kelvin. And so close to the stars, I mean, it will be very hot and all of your gas is ionized and no dust can survive because it's completely broken down. But if you travel further away from the stars, we are going to probe probably down to temperatures about 60 Kelvin or so. So we have a very, very large temperature range that we cover with our observations, and we can see how things change as you go at lower temperatures.
Thank you.
My question is the last question. You were using the mirror paradigm and talking about the optical or the visual spectrum, but what kind of mirror do you use in the infrared spectrum? Is it a very similar mirror, or what is the material used for an infrared mirror?
So the Webb's mirror, is made from beryllium because it's very light and very sturdy. And you know, if you have to support something of 6.8 meter diameter, it's big, no? So it has to be very stable, not subject to temperature changes too much, because you know, once the mirrors are aligned, you don't want, because if the temperature changes, that things, you know, moves around again. And there is a gold coat on top of it, because then the radiation gets reflected to the secondary mirror. So I'm not sure if I shown you in a little image here, you see the gold coat clearly. That's the big mirror. That's the one that's 6.4 meters diameter. But you have this structure that holds up a secondary mirror, which is much smaller, which is at some distance in front of the big mirror. And so the big mirror collects the light and reflects it to that secondary mirror. That secondary mirror reflects it back to the instruments. And so that gold coat is to enhance the reflection, so that whatever photon or light hits the mirror, we actually can bring to our detectors, and we don't have too many losses.
Thank you. And I think that is it for our question and answer time. Els, we would like to thank you, the Rotary Club of London, and in recognition of your presentation to our club today, we will be making a contribution to the Polio Plus campaign of the Rotary Foundation. Because of you, Rotary is one step closer to making the world polio free. So thank you very much. Very interesting presentation today.
Well, thank you all for your attention and your interesting questions. And I think this is a really nice idea, this donation. Thank you.
So we will now proceed with club business. The first item is, we've talked about this, I think, last week, a special presentation tomorrow night on the Ukraine. Tatiana, who is a former Rotary Youth Exchange student, as well as the past president of the Rotaract Club at Fanshawe, will be speaking to our satellite club meeting tomorrow night at 6:30 p.m. You will be receiving a club runner email sometime this afternoon with the Zoom link for that meeting, for that presentation. If you are interested in attending it, that same email with the Zoom link will also include the links for different ways to contribute to various causes in the Ukraine. The first one is the Rotary International, the Rotary Foundation Disaster Response Fund, which is accessible by districts in the Ukraine and bordering on the Ukraine as part of the Rotary response to what is going on in the Ukraine and the millions of refugees leaving the Ukraine and in the neighboring countries. The other link will be for Shelterbox, which many of you are probably familiar with and is a Rotary partner, and the emergency shelter that they're providing in both the Ukraine and in the neighboring countries. And the London Ukrainian Center, or London Ukrainian Community Center, they were looking for donations of many different things earlier this month, but right now they are only able to handle financial contributions. That will probably change once refugees start arriving in Canada, but they don't have an ETA for that yet. But I will be including the link for that in the email. The other quick announcement, I don't think Randy's here, so I'll make it for him. We are still looking for one host family, I believe, for our exchange student that will be arriving at the end of August. Nanda is a female student coming from Switzerland, and she will be attending high school here in London for the upcoming year. I think Randy's got the other two host families lined up. We're just looking for a third host family. If you have never hosted an exchange student before, it is a really fun, interesting experience. You will learn something in the process. You will learn many things about the country that the student comes from, but you will also learn many things about Canada, because they will ask you lots of questions that you realize you do not know the answer to, and you have to go look up the answer about Canada as to why things are this way so that you can answer it. And it's a lot of fun. So highly recommended if you are interested in a great opportunity. Are there any other announcements for the good of the club? If not,
Don,
yes.
I do have two announcements. First, at our last Rotary meeting, if you have the membership recollect, we decided on going forward with the reorganization of our meeting structure. And as a result of that, at the board meeting, there was a special task force committee struck that's going to, that I have captioned the BIPC, which stands for Back In-Person Committee, to work out the logistics of how we're going to roll out, at least for the first 6 months, the new reorganization and structure. On that committee are Jan Delaney, Steve Knox, Julie Pontus, and Sherrod Ray. And we're going to be having our first meeting via Zoom tomorrow at noon. Unfortunately, Sherrod is away on vacation, so he won't be able to join us. But I anticipate that we will be meeting weekly until we get something that we can recommend to our next board meeting, which is April 20th. The second announcement I want to make relates to Rotary Bingo fundraising. I'm delighted to advise the club that we are going back to full 7 days a week bingos. The bingo hall will be opening, and as a result, there will be bingos available on Mondays and Tuesdays. And our club has picked up 2 more bingos. So we're going to have 1 bingo a month starting in April, running one in April, 1 in May, 1 in June, and 1 in July, which is great to reestablish that fundraising avenue.
I will just bring up our final slide for today before we let everyone go. And that is a quick bunch of reminders about what is coming up in the next little while. So our meeting next week, we will have Brianne Curry from Autism Ontario speaking. A reminder once again, tomorrow night, 6:30, Tatiana will be presenting at the Satellite Club meeting, talking about the Ukraine. We are 1 month away from our next board meeting. Cocktail hour still is going on, Tuesdays at 5 p.m. Coffee Clutch is still going on, Thursdays at 10:30 a.m. The last thing I want to remind everyone is that, yes, we in Rotary serve to change lives, and hopefully everybody will have an opportunity to do that sometime over the next week until we meet again.